some problems that involve the relative motion between two objects, and we'll use translating axes for the analysis. To determine the relative motion, the first thing you should do is establish the xy axes. And then you can write the relative motion equation between the two objects, A and B. For example, here, the equation states that the velocity of B is equal to the velocity of A plus the velocity of B with respect to A. Notice the notation. The A here will cancel with this one, and it sort of leaves us with the B here to sort of be in agreement with this B. I only mention this so you'll have a quick way to remember how to set up the equation. The second equation, of course, gives us our relationship between accelerations. Once these equations are set up, then you can resolve each of the vectors that go into each of the terms here into their x and y components, and solve the two scalar component equations for the two unknowns. We'll do some problems now to show how this all applies. We'll begin with this one. We want to determine the velocity of the car B relative to A. Well, of course, the first thing to do is to set up our x and y coordinate axes, and they look like this. Next, we'll write the equation between A and B, our relative velocity equation, and this is the term we're trying to find. Now we'll put the data into the equation. Underneath each one of the terms, we'll label the vector magnitude and direction, starting with the velocity of B. Its magnitude is 40 meters per second. Now we have to determine its direction. Actually, you can determine it rather quickly. If I draw a horizontal line in here, the angle right in here will have to be 60 degrees. And the reason that's so is because when this angle closes up, or this line OB goes to the vertical, closing the angle of 60 degrees here, the arrow will be brought back up to here, to the horizontal, and it will close up the same angle. That's how I know this to be 60. If you don't like doing it like this, you can also extend a line from the car back to the vertical line and form a right triangle right in here. This angle, of course, is 30 degrees, and therefore the angle from here being 90, this angle in here is 60 degrees, and therefore the angle over here must be equal to 60 degrees. In other words, if I extend this, I think you'll agree we have a 60-degree angle in here. All right, so let's put our data in the equation and see what happens. First off, let me put in our V sub B. As we stated, this angle is 60 degrees. And of course, the magnitude of the vector is 40 meters per second. Now we set that equal to V of A. There we have a horizontal velocity, and it's moving at 10. And finally, we have our two unknown vector components for V of B with respect to A. I'm going to assume them to be always going in the positive directions. And so therefore, I'll write this one as being V of B with respect to A in the horizontal direction. So we'll say V of B with respect to AX. And finally, we have the other one assumed to go positive upward. And we refer to that as V of B with respect to A in the y direction. Now all the terms are indicated in our equation. Now we need to write the component equations. Beginning in the x direction, taking each vector component in turn. We have first 40 times the cosine of 60 degrees. And we set that equal to, here we get 10, of course. And we have positive V of B with respect to A in the x direction. And here, of course, there's no contribution. You can write a 0 in here if you care to, but it's just redundant. Anyway, when I solve for V of B with respect to A in the x direction, I get this answer, and it turns out to be positive, and so the arrow goes the way you see it here. Now we'll sum in the y direction. There we have minus 40 times the sine of 60 degrees. That component goes downward, of course. That must equal nothing from here, nothing from here, and therefore we just simply have on this side v of b with respect to a in the y direction. When you do the calculation, you get your result. It turns out to be minus 34.64, so it goes downward. We need to find the magnitude of this. And how do you find it? Well, Pythagorean's theorem, correct? In other words, the square root of 10 squared plus 34.64 squared. 36.1 meters per second. That's how fast B will be moving when seen by the driver of A. And the direction in which B will be moving relative to A can be determined also. We can refer to that direction, for example, from this horizontal line. And to find it, of course, you would just simply say this angle is equal to the arctangent of this side, 34.64, divided by this side, 10. Looking up that angle will give us our result, although here I'm just simply reporting the magnitude. All right, now let's consider the same two cars, except here we want to find the acceleration of B relative to A. At this instant, A is still moving along a straight line path, and so its acceleration is simply defined by this term. B is moving along a curved path, so it'll have actually two components of acceleration. This component, of course, is the tangential component. It's indicating the change in the magnitude of the velocity, and it goes down this way, of course. The other component is the normal component, and it goes in toward the center of curvature. It represents the change in the direction of the velocity vector. All right, let's set up our axes first, and now our relative acceleration equation. So now we'll put the data into it. First, we'll consider the tangential component of acceleration, 30 meters per second squared, and of course it goes down at this angle of 60 degrees, just as we discussed previously. So let me set that up. This is 60 degrees. And as we see from the problem, it's 30 meters per second squared. Now we have the normal component. And that goes in toward the center of curvature. And so the angle made right in here will have to be 60 degrees, won't it? Just like this one. So here we write it as follows. Where this is 60 degrees. And our term, of course, is v squared divided by rho. Or in other words, it's 40 squared divided by 40. And we set this equal to A of A, which happens to be 3 meters per second squared, horizontal. And now our two unknown acceleration terms. We have A of B with respect to A. That's in the x direction, positive going to the right. And finally, our vertical component, which is A of B with respect to A. And that's y, and it goes upward, positive. Now we'll set up our component equations to complete our solution. So considering this term first, we have 30 times the cosine of 60 degrees minus the component from this one. When calculated, becomes 40, doesn't it? So we write it as minus 40, and that's times the sine of 60 degrees. and it's equal to 3 here, and plus a of b with respect to a, x. And no contribution from this term. Finally, in the y direction, we have minus 30 sine of 60 degrees we have minus 40 cosine of 60 degrees, and all this equals nothing from here, of course, and from here, plus a of b with respect to a. And of course, that's in the y direction. And now that I've got my two component equations written out, I can solve them, and I'll get these results, the four significant figures. And you can see this one goes to the left because the calculation gives us a negative answer. And this one also gives me a negative answer, and so it indicates that this component is going down. When I add these up vectorially, like you can see here, I'll get my resultant acceleration. And that's found from Pythagorean's theorem, isn't it? Turns out to be 51.3 meters per second squared. I can also define its direction if I care to. Say, for example, from the horizontal. The tangent of that angle, of course, is equal to the opposite, 45.98, divided by the adjacent, which of course is this vector, 22.64. And then you get theta. Before we end the lesson, let's just do one more problem for practice. Here we want to determine the components of the acceleration of the boat at B relative to that at A. Here you see A is moving along a straight line, so its acceleration is defined simply by this term. B moves along a curved path, and so there are two components of its acceleration. The tangential component shown here, which is the change in magnitude of the velocity vector, and the normal component, which is directed down this way, the change in the direction of the velocity vector. We'll set up our axes like this, and now our relative acceleration equation. So at B, we have the two terms, the tangential component of acceleration, which is going to the right, and we have the normal component, in other words, b squared over rho, or in this case, 20 squared, divided by 10, and it goes down toward the center of curvature. And we set all this equal to a of a. Now this vector is going down this way, and the angle right in here, of course, is going to be 45 degrees. As you can see, when this closes to 0, the boat will be brought up to here, and it will close this angle up here, which is, as I said, 45 degrees. Now that we know the direction of the acceleration, and we know its magnitude, let me put that in our equation. We have 20 meters per second squared, and our angle, as I've said, is 45 degrees. And finally, we have to add to this our unknown two components of acceleration of boat B relative to A. A of B with respect to A in the x direction, and we say that is positive to the right. Always put these in the positive direction. If you get negative answer, it simply means it goes in the other direction, right? A of B with respect to A in the y direction. Which way does it go? Upward, positive. So summing in the x direction, we have 10. So we set it equal to, from here, of course, a negative result, minus 20 times the cosine of 45 degrees. And then here, of course, we have plus a of b with respect to a in the x direction. We can solve this and we get our result of 24.1 meters per second squared. And it's positive, so it goes this way. And finally, one more equation. And here we have a term which is negative, don't we? So we write minus 40. I hope you see this would be minus 40 when you do the calculation. And it's equal to, from here we have a negative term, minus 20 times the sine of 45 degrees. And from here we have a plus term. That would be a of b with respect to a in the y direction. Boom. Now we can solve this equation, and we get an answer which is minus 25.9 meters per second squared. So it goes downward. And as in the previous problems, if you wanted to find the actual acceleration of b with respect to a, you would add these two component vectors. Let me just show that for you. If these are carried out to more significant digits and you work it out, you get 35.4 meters per second squared. And again, taking the two components and doing a little graphic like this to show the vector addition, you can find the angle that this resultant acceleration makes, say, with this horizontal line. Anyway, having ended this problem then, we'll finish the lesson.